We're going to talk about the exponential and logarithmic functions today. What is an exponential function? Basically, it's a function that can be written with a base b and a variable in the exponent. The simplest form of what we want to look at is something to the effect of f of x equals b to the x. Again, when we see the x in the exponent, we automatically classify it as an exponential function. B is just a constant, okay? It could be any constant. It could be a 5, it could be a 2, it could be a 1/2. But we want to look at it in the general term to begin with. Examples of exponential functions. We have f of x is 16 to the x power, f of x is square root of 2 to the x power, and f of x is 1/8 to the x power. Again, just emphasizing that our base can be any number we care for it to be, and again, our variable is in our exponent. Now, we do have properties of exponents, rules for exponents that you learned way back in algebra. We do know that if we have the same base and we multiply two numbers with the same base, we add the exponents, so b to the m times b to the n is b to the m plus n. Similarly, if we divide two numbers with the same base, b to the m divided by b to the n, we subtract the exponents. That equals b to the m minus n. And one of the last ones is if we raise a base to an exponent, so if we already have, we raise a power to an exponent to a power, so b to the m to the n power, we wind up multiplying. So this is b to the m times n power. We're going to apply this last one in our next slide. We want to understand that if we have b to the m, if we have a base to an exponent, we raise it to a power, we're going to multiply the two exponents. Let's go back to our original examples. We had f of x was 16 to the x, f of x was root 2 to the x, and f of x was 1/8 to the x power. What we want to do is we want to rewrite these in the form 2k to the x. In other words, we want to change the base to 2. So if we look at 16, we realize that 16 is just 2 to the 4th power. So I can rewrite 16 to the x as 2 to the 4th to the x power. And if you remember, our last property says if I raise a base to a power, and then, if I raise an exponent to a power, I just simply multiply. So this simply becomes 2 to the 4x. All I'm doing is multiplying exponents here. And the real key was just rewriting this 16 as 2 to the 4th. Now I've rewritten this as 2 to the kx power. In this case, k is 4. Some of these are a little bit trickier, but are still doable. If we recognize this is the square root of 2, square root is the same as the 1/2 power, so I can rewrite this as 2 to the 1/2 all to the x power, which becomes 2 to the 1/2 x power. Again, what we're trying to do is just manipulate to get the same base. Once we have the same base, things are a lot easier to work with. And we will look more at that later. 1/8, this is maybe the little trickier one because we don't see a 2 anywhere, but we do realize 8 is 2 cubed, and since this is in the denominator, 1/8 is 2 to the negative 1/3 power. So again, applying our exponent to power property, this becomes 2 to the negative 3x power. Let's look at something a little bit more complicated. I want to do the same thing. I want to rewrite these in the form 2 to the kx. Well, I have 16 over x in my numerator. I have 2 times 2 to the negative 4x in my denominator. I'm just going to follow the properties I know. We're going to do what we did in our previous slide. Let's write everything to the power of 2. So this becomes 16. We know from our previous slide is 2 to the 4x power. And we also know from our rules for exponents that when I multiply, I add exponents. Well, this is 2 times 2 to the negative 4x. This is just 2 to the first power. So this becomes 2 to the 1 minus 4x. Now we're going to apply our last rule. Our last rule says if I have the dividing numbers with the same base, I subtract exponents. So this is 2 to the 4x and 2 to the 1 minus 4x. I'm going to subtract exponents. I need to remember to distribute this minus into everything. So 4x minus 1 minus 4x. This becomes 4x minus 1 plus 4x, which is 2 to the 8x minus 1 power. We also want to be able to solve exponential equations. Our basic solutions, if the bases are equal, the basic idea is if I have the same bases, I'm going to simply set the exponents equal to each other and solve. Well, I have 9 to the 4x equals 9 to the 12th power. Well, notice my bases are both 9, so all I'm going to simply do is get rid of the bases and just look at the exponents. I'm going to set 4x equal to 12, so x is equal to 3. And when I plug 3 back in, we should clearly see that the left-hand side becomes 9 to the 12th power as well. What happens if the bases aren't equal? Well, one of the simple tricks is to try to write them as the same base. So I have another problem. 7 to the 2 minus 4x equals 49. Well, one of the things that should occur to us is that we do know that 49 is 7 squared. So I can rewrite the right-hand side as 7 squared. Now I have the same base, and I can take the same approach I did before, was once I had the same base, I just take my exponents and I set them equal. So 2 minus 4x is equal to 2. And clearly the 2's are going to cancel and you get negative 4x is 0, so x is 0 is my final solution. Now we do have what's known as the natural exponential function. This is f of x equals e to the x. E to the x is actually a number, I think it's 2.718, etc. It's kind of like pi. It's an irrational number. It never repeats itself. However, it has a very powerful property in the fact that the derivative of f(x) equals e to the x, f prime of x is equal to e to the x as well. In fact, it's the only function minus the function y f of x equals 0, a horizontal line, whose derivative is itself. Let's practice taking these derivatives. Well, we did this in our previous lecture. But when we take the derivative of e to the x, this is one of our rules. We could look at this and say we want to use a quotient rule, or we could recognize I could divide and separate each of these fractions out and take the derivative separately. The derivative of 3/5 x is just 3/5. Derivative of 8/5, the derivative of constant is 0. And this is negative 2/5 times e to the x. And we know when we have a constant, we don't take the derivative of it. If it's multiplied by a function, we just carry the constant down and then take the derivative of the function. So the derivative of e to the x is e to the x. So our final answer is just 3/5 minus 2/5 e to the x. Now our next one is we have f of x equals the square root of e to the x minus 1. We do realize we can rewrite this as e to the x minus 1 raised to the 1/2 power. Now, we studied the chain rule in our previous lecture, and your chain rule says you take the derivative of the outside, leaving the inside alone, and then you take the derivative of the inside. So if I take the derivative of the outside function, which is the 1/2 power, I bring the 1/2 down, subtract 1 gives me a negative 1/2. I leave the inside alone to begin with, and then I multiply it by the derivative of the inside, and the derivative of e to the x minus 1 is just e to the x. Now we can rewrite this if we wanted to. We know this negative 1/2 puts this in the denominator and makes it a radical. And then we just bring the e to the x up top. So notice all I did here, I rewrote the e to the x minus 1 to the negative 1/2 power. As the square root of e to the x minus 1, I put it in the denominator. I put the 2 in the denominator, and then I brought the e to the x up top. If you remember from our chain rule, our basic rule was the derivative of e to the u was e to the u du dx. And we assumed u was a differentiable function of x. And what we did is we just took the derivative of e to the u, brought it e to the u down, and then multiplied by the derivative of the actual exponent, the exponent, whatever the function was in the exponent. Let's take some practice. We've already practiced with this a little bit. Say the derivative of y is negative 4 e to the negative 3x. Again, we bring the negative 4 down, we bring the e to the u down, and then we just take the derivative of u, which in this case is negative 3, and we just simplify. Negative 4 times negative 3 is 12, so this becomes 12 e to the negative 3x. Similarly, if we have a polynomial in our numerator, or excuse me, in our exponent, we can do the same thing. Derivative of e to the u is e to the u du, so I bring this e to the u down and multiply it by the derivative of the exponent. The derivative of the exponent is 3x squared minus 10x. And again, we're just going to multiply this out. This is 3x squared minus 10x times e to the x cubed minus 5x squared. Some of you may question, well, what's the difference between step 2 and step 3? Really nothing. We just typically put the derivative, our du dx, out front to simplify it. Alright, take the derivative of the following function. Now here is a situation where we're going to have to use our quotient rule. We have 6 e to the 4x in our numerator and 8x minus 1 in our denominator. We have two variables 1 in the numerator, 1 in the denominator, so I cannot just split this up and make separate fractions out of it and do what we did in our previous problem. So if you remember, your derivative, your quotient rule is low times the derivative of the high. The derivative of 6e to the 4x is 6e to the 4x times the derivative of the 4x, which is just 4, minus high d low, and the derivative of 8x minus 1 is just 8, all over low squared. Now we want to simplify this, and I want to encourage you when you're taking derivatives of these exponential functions. One of the easiest way to simplify is try to factor things out. And if you look at this first, this is my low d high and my high d low. Notice they each have a factor of 6e to the 4x. So I'm going to factor that out. And then I have a factor of 4 and a factor of 8 here, so the greatest common factor is 4, so I'm going to pull out an extra factor of 4. So I'm actually going to factor out 6e to the 4x times 4, which is 24e to the 4x. That's going to get rid of all of this. It's going to leave me with 8x minus 1. And it's going to get rid of most of this and just leave me with a 2 because I pulled the 4 out of the 8. So I'm left with 8x minus 1 minus 2 in my numerator, which is 24e to the 4x times 8x minus 3 all over 8x minus 1 quantity squared. Again, we're just building on the rules we've already studied. It is important that you work towards mastery on these rules so that you can pull on them, use your arsenal of tools when you need them. Let's look at an example. Let's tie this back into what we already know about derivatives. It says a work of art purchased in 1980 for $25,000 is estimated to be worth, this value v of t is 25,000 e to the t over $10 after t years. At what rate will the work of art be appreciating in 2010? The way these exponential function works is that you have a beginning value, and at time 0, if you want to think about this, e to the 0 over 10, any base to the 0 power is just 1, so at time 0 we start out with the initial value of the artwork, which is 25,000. And this is how its appreciation is growing exponentially. It says at what rate? Well, we do know that derivatives give us a rate of change. So what we're going to do is we're going to start with our original function, and we're going to take the derivative. And we know the derivative of e to the u, we're going to bring the 25,000 down. E to the u, du. Well, du in this case is 1/10. So 1/10 of 25,000 is 2,500. So my derivative is simply 2,500 e to the t over 10. When you have a simple function like this, one of the easiest ways, instead of taking in 2 steps, is just take the derivative of this exponent and multiply it by what is out front, which is really what we're doing because we're going to take the derivative and then we're going to bring that out front. So we're just doing it in one step. So now I have the derivative of our value function. Now they want to know what the rate will the artwork be appreciating in 2010. Well, I started in 1980 and I'm measuring t years after 1980. So I'm measuring 30 years into the future. So I'm going to plug in 30 for t. I'm going to get 30 over 10, which is just gives me 3. So I'm going to have 2,500 e cubed. So I wind up with $50,213.84. So basically, to interpret this means that the work of art will be appreciated at a rate of literally over $50,000 per year in 2010, which is a nice return on the investment for something that was purchased for $25,000 back in 1980. We're going to get briefly into what's called as differential equations. We're only going to do a handful of problems here. We're not going to linger. Basically, we're going to give you a very simple form. For any equation of the form y prime equals k to the y. So I have a situation where a derivative is equal to a multiple of the original function. All solutions are of the form y equals c e to the kx. So we're going to be given that k originally, and we're going to know that the solution is y equals c e to the kx. Well, let's look at an example. Determine all solutions of the differential equation below. I have y prime equals negative 4y. Well, in this case, I know k is negative 4. So my solutions have to be in this form. Y equals c e to the kx. We know k is negative 4, so my solutions are y equals c e to the negative 4x. This is my actual answer. These are all solutions of this differential equation, okay? Now, if I was given an initial value or a specific value, I could plug in and solve for c. We're not given that here. So this tells me all general forms to this equation, all solutions occur in this form. Well, how can we check this? Well, to check it, we can actually differentiate what we got for y. And if we differentiate what we have for y, we have y equals, this is c e to the u times du, so negative 4 c e to the negative 4x. So if we plug this back into our original equation, here's the left-hand side is equal to this. But if you look at the right-hand side is just negative 4 times y, and this c e to the negative 4x is my y, so my left-hand side does most definitely equal my right-hand side. Again, we don't have to, I'm taking this extra step to show you why it works, but really we're going to stop here because this is our answer for the differential equation. Y prime is negative 4y. I want to talk briefly, transition over to the natural log. The natural log is just your typical logarithm. It behaves like every other log you studied. It's just different in the fact that it's base e instead of base 10 or base whatever. The properties are still the same. We know the natural log of a times b. If I'm multiplying two things inside my log, I can split it up, and it's equal to the natural log of a plus the natural log of b. Similarly, if I'm dividing two things in my log, the natural log of a over b is equal to the natural log of a minus the natural log of b. And finally, if I'm raising a power inside of a log, the natural log of a to the k, I can bring the k out, and it's equal to the natural log of a. Now please understand, whenever you see these equal signs for these properties, they go both directions. So I can go left to right or right to left on any of these properties. Let's see how some of these properties work. If I want to simplify this, the natural log of 8 plus the natural log of 3 minus the natural log of 6. I can actually combine these into a single log. Your rule says that when you add logs, you multiply, and when you subtract, you divide. So this is equal to the natural log of 8 times 3 divided by 6. Well, we can simplify the numerator, which is 24 divided by 6, and then reduce that just to the natural log of 4. So I can take this entire equation and reduce it to simply the natural log of 4. Similarly, if I have something like this, 1/3 natural log of 8, we do, like I said before, the properties work left to right and right to left. This 1/3 can be brought inside the log, and this becomes the natural log of 8 to the 1/3 power. Well, we need to carry this out a bit further because the cube root of 8 is just 2, and this becomes the natural log of 2. Basics of our natural log function. Why are our natural log function important? Well, the natural log of x, which is the natural log function, and e to the x, which is the natural exponential function, are inverse functions. They basically undo each other. So if I look at the natural log of e to the x, since they're inverse functions always undo each other and leave you what you began with. So the natural log of e to the x is just equal to x, because I hit the x with the e and then I undo it with the ln, and so I'm just left with what I began with, which is the x. Similarly, e to the natural log of x is equal to x as well. Again, I hit it with the natural log, then I hit it with the e, and they undo each other. Let's simplify the following. I have the natural log of e to the 7th. Again, the natural log and e are inverse functions, so they undo each other. So our final answer is simply going to be 7. This one is a little bit more complicated because even though we see the e and the ln, there's a 3 in between here. I have e to the 3 ln of x. I can't just assume that they undo each other right away. They have to come back to back consecutively. So I needed to find a way to either get rid of the 3 or move the 3. Well, if we just look at the exponent, the 3 ln x, I can rewrite 3 ln x to ln x cubed because this 3 can be brought inside and made an exponent. Well, now I have the e and the ln hitting consecutively, and so they undo each other. I'm just left with what's remaining, the x cubed, and that's my final answer, x cubed. Let's look at another example. If e to the x equal to 6, write in terms of natural log. In other words, I want to remove the e to the x and get a natural log into this equation. Well, I'm going to start with my original equation, and then what I'm going to do is I'm going to use the properties of all equations. Your properties say whatever you do to one side, you can do to the other, and it doesn't change your solution. So what I'm going to do is I'm going to hit both sides with the natural log function. So the left-hand side is going to become the natural log of e to the x. The right-hand side is going to become the natural log of 6. Now the nice thing about it, remember what we said, they undo each other. So the natural log and e undo each other, and the left-hand side just becomes x. So x is equal to the natural log of 6. So now I am done. I have written this in terms of the natural log. I've converted from one form to the other. These two forms are equivalent. Let's look at solving the following function. I have e to the 3x is equal to 12. If you remember, we started solving exponential functions. We said let's try to match bases. Well, a lot of times we can't match bases, okay? So what do? Well, this is where our logarithms come in. I notice I have e to the 3x. Well, I do know that the inverse function of e is the natural log. So I'm going to hit both sides with the natural log. What that's going to do is that's going to get rid of the e and just leave me with the 3x on the left-hand side. I'm going to get 3x is equal to the natural log of 12. So x is 12 natural log, 1/3 natural log of 12. Now, please don't multiply the 1/3 into 12. That's not allowed because you can't distribute this in. What we could do if we want to take it a step further, which I didn't in this case, I could write this as the natural log of 12 to the 1/3 power. I could bring the 1/3 in as an exponent. Let's talk about the derivative of the natural log function. We do know that I have a function f of u is the natural log of u, and we're going to assume u is a function of x. The derivative of the natural log of u is equal to 1 over u times du dx. In other words, I take whatever's inside of the natural log, I drop it down into my denominator, and then I multiply it by the derivative of what was in the natural log. Let's look at a couple examples. I have f of x equals ln of 4x plus ln of 5. A couple things to begin with. Don't get tripped up when I see something like this ln of 5. When I take the derivative, ln of 5 is still a constant. Notice there's no variable here, so when I take its derivative, it's still going to be 0. My derivative of natural log of 4x, this is my u. I'm going to bring it down to the denominator. This is going to be 1 over 4x times the derivative of 4x is just 4. Again, the derivative of natural log of 5 is 0. So when I simplify this, 4 times 1 over 4x is just 1 over x, and that is my derivative of the natural log of 4x plus the natural log of 5. A slightly more complex example, this is a natural log of a polynomial. The polynomial in this case is x squared minus 5x plus 7. Our properties still apply. This is my u, so my derivative is going to be 1 over u times its derivative du dx. So it's 1 over x squared minus 5x plus 7 times 2x minus 5, which is just 2x minus 5 over x squared minus 5x plus 7. You're actually able to go straight from the first step to the last step if you want to, and just put the derivative of u over u, and that is actually the derivative of the natural log of u.